So hi guys, today I'm just going to go over a couple, really just two examples of proof by induction. The first one will be about the sum for the formula for a geometric series, which I had kind of pointed out would be a good one for you to try on your own, in case you did, or even if you didn't. I think it's useful to see that proof. And then we're going to check out some other other proof about an induction formula where it's not something like of the sort we've been doing. That you notice every proof I've done so far has been some summation formula equaling, a result. But you can use induction in other scenarios, so I'm going to do one of those too. Anyway, let's start with the geometric series argument. Now, that word is actually, if you've been in calculus, you'll know this is a technical way to describe those summations we talked about. So you have a sequence, it's a list of things. If you have a series, it's add up a list of things. So the sum we're after, the geometric series we're after, is going to look like this. It'll have some number, usually called r, raised to the I power. And I is the index for the sum, so you'll go from 0 to n. Right? If I were to write this in expanded form, which probably would be smart, when the index is 0, or anything to the 0, that'll be 1. And when it's 1, you'll get r, then r squared, and so on, right? Higher and higher powers on the r, and we'll end with r to the n. R to the n. Sorry, I was about to say plus 1, but no, r to the n. Okay, so what is this? It turns out the formula, or a formula for that expanded sum is the following. It's r to the n plus 1 minus 1 over r minus 1. There's proof of this that doesn't involve induction, but is a little bit hand-wavy, and I think it can be made into a precise one. So I'll show you this argument first, and then we'll do the inductive proof. It's actually kind of nice to be able to prove a thing in more than one way. So there goes. If you write s for that sum, and we'll keep the expanded form of it, 1 plus r, whoops, not r squared yet, r to the 1 power plus r squared plus dot dot dot. Plus, let me throw in r to the n minus 1, and then finally r to the n. Okay? If we call that s, then if I multiply s times one more copy of r, what's that going to do? It's going to give you r plus r squared plus r cubed plus dot 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 plus, here we'd have r to the n power, right? And then finally we'd have r to the n plus 1. Yay? And the reason for making these, we're writing these two things out next to each other, is you'll see the kinds of cancellations that'll happen if we subtract. There's an r in this one, and there's an r in that one, an r squared, and an r squared, an r cubed, and, well, it's not there, but it's in the dot dot dots. There's an r cubed. There's an r to the n that cancels with that one. Back in the dot dot dots of this one, we got an r to the n minus 1. So if I subtract them, most of the stuff will go away. If I take rs and subtract s, I will get r to the n plus 1 survives, because it doesn't have anything that it pairs with, but everything else gets killed, and then, well, in the end, there's nothing in the bottom of an rs that has a 1 in it, so we get r to the n plus 1 minus 1. A lot of collapse, right? This will just barely fit on the board, so you can factor s out of that. And then what would be left is r minus 1, so r to the n plus 1 minus 1, let me just write it in the slash form, we'd be dividing by r minus 1. Which is, what I said was the formula, right? So that's a pretty convincing argument, I think. There is an issue in it when I when I did the when I did the division, I divided both sides by r minus 1. I need to know that that's not a 0, that you can, in fact, divide by that, which is pretty reasonable if you think about it. If r was equal to 1, this would be 0, but r equal 1 means this is just 1 plus 1 plus 1 plus 1 up to 1 to the n. And we don't really need a formula to work out that sum. It's actually n plus 1. So I erased the board, and then I thought, let me write up a nice clean version of the theorem we're trying to prove. It's quantified over all natural numbers and all real numbers except for 1. And if you look at it, the formula we're trying to prove for the sum of the geometric series is nonsensical. If r is equal to 1, you end up with 0 over 0. Right? But other than that, this formula holds. So what's the proof going to look like? Well, it's said by induction, so you're expecting to see two phases. You're expecting to see a base case, and that is the smallest value that makes sense, or sometimes it's the smallest value even if it doesn't make sense. But for this, n is equal to 0 actually is reasonable. That would be the sum has from 0 to 0. In other words, it's just got one item in it. And that item is r to the 0 power. So in doing the base case, you're just going to verify that the sum is equal to the formula for n equals 0. So yeah, base case is n equals 0 in this particular instance. They can be other things, but this time it's n equals 0. So sigma I equals 0 to 0 of r to the I is simply equal to, well, it's got a 1 term and it looks like r to the 0, which is 1. And the formula, when n is equal to 0, is r to the 0 plus 1 minus 1 over r minus 1. And that's equal to r minus 1 over r minus 1, so that's also equal to 1. And those two things together, or those two things both coming out to the same answer, that verifies the base case. All right, so we're good on the base case. Let's see how the inductive step is going to work. First, you're going to clearly label this as being the inductive step. And then proceed. Well, how does the inductive step work? You're supposed to assume the if part and then prove the then part. This is just maybe as a reminder of what we're doing in this step. We're taking the kth version of our formula and seeing if we from that can deduce, or we're trying to deduce from that, the k plus first version. That's what we're after. So assume that k is a particular but arbitrarily chosen natural number bigger than 1. You don't have to say all those words, but it gives a sketch of it. Assume k greater than 1 is arbitrary, and that the formula we're after works for k, which means that the sum, which goes from 0 just up to k of r to the I, whoops, I was about to write I to the r to the I, that indeed will be equal to r to the k plus 1 minus 1 over r minus 1. That's the inductive hypothesis. Okay. Now, what do we add to both sides in order to make this sum go one stage farther? You just add r to the k plus 1 to both sides. And if you do that, I mean, the reason I picked r to the k plus 1 is I wanted this sum to go from 0 all the way to k plus 1. Right? So I'll have I equals 0 to k plus 1 now of r to the I. I can't quite do such a nice bit of trickery with the other side, though, so I'll just write it as, well, what we've got, r to the k plus 1 plus the formula that was there before, r to the k plus 1 minus 1 over r minus 1. And from here, it's just going to be algebra. We eventually want this to look like that formula, but with a k plus 1 in it. So we're trying to get it to look like r to the k plus 2 minus 1 over r minus 1. How's that going to work? Well, I think the only thing you could do with two things like this, get a common denominator and see if you can add them together. R minus 1 will be that common denominator, so that's equal to r to the k plus 1 times r minus 1 over r minus 1 plus the formula that was already there on the other side, r to the k plus 1 minus 1 over r minus 1. I just noticed I did need this set of parentheses on this one, but this bottom is already grouped by the fraction bar. The fraction bar deserves to do that, so technically those other parentheses weren't needed. It's the same thing, but anyway. Well, we've got just a little bit of algebra to work out to get down to the final thing. Maybe I can just put it at the top of the board and not erase everything up to that. So this looks like r to the k plus 2, right? Because r to the k, we're just going to distribute this r to the k plus 1 over the other thing. So we get r to the k plus 2 minus r to the k plus 1 plus r to the k plus 1 and then minus 1. All of that over r minus 1. Right, so the two things in the middle cancel each other and we get exactly what we were hoping for. R to the k plus 2. Let me write it this way though. It's r to the k plus 1 plus 1 minus 1 over r minus 1. And that's the inductive conclusion. So we've proved the base case, we've proved the inductive step. The result follows by induction, by the principle of mathematical induction. I don't think that you have to do this every time, but just this once, I'm going to give one of those summation sentences so that you know, you can feel like you can write this out in very good form with all your I's dotted, your T's crossed, right? So since the base case is true, fancy, I can say we have verified it. Does verified end up with no? I might be spelling that word wrong. I'll check later. Since the base case has been verified and the inductive step has been proved, our result follows by the principle of mathematical induction. I would just, that's very commonly abbreviated as PMI, so, and especially since I only have a little bit of space left on the board, I'm going to abbreviate it. And there you go, we can say QED. There are several other sort of general types of statements that are proved by induction. Inequalities, divisibility things, lots. But I think there's a whole category of divisibility statements that tend to get mentioned at this point when people are talking about proving things by induction, because they're so easy to cook up examples if you know a trick. So this is like the math professor. I'm giving you a peek behind the curtain right now. Math professors all know this trick, and so they think they're being clever, coming up with a bunch of proofs that they can stick their discrete math students with. So I'm going to show you the trick. It's a thing called Fermat's little theorem. Fermat was a French attorney, lawyer, avocat, who was called the Prince of Amateurs. He came up with a lot of things, a lot of theorems. He proved quite a few of them. He was mistaken in a very small number of instances, but and he's probably most famous for a thing called Fermat's last theorem, where it was something discovered in his one of his notebooks after he died, and he made this claim that he had a miraculous proof for a statement that he made back in like the 1600s. It finally got settled in the 1990s. So yeah, it was one of those real moments where, you know, a 400-year-old theorem finally got cracked. It's probably not the case that Fermat knew about the correct proof of his last theorem, but his little theorem is easy to verify, and it's definitely true, and we know he proved it. And it's this: if p is a prime number, then any number raised to the p power is the same congruence class as x is if you do things modulo p. So this is the notation for saying that two things are in the same category mod p. That is, if I figure out what x to the p is and take its remainder mod p, and I figure out what x is and get its remainder mod p, those numbers would be equal. So that's it's not quite the same as saying they're equal, so we use a different symbol there, but it's definitely a lot like being equal, so hence the similarity with that to the regular equal sign. So that's Fermat's little theorem. You probably want some examples of this. How about if I take, for instance, x is 2 and p is 7. Then x to the p is 2 to the 7 power, which is, 2, 4, 8, 16, 32, 64, 128. All right, and x is 2, so that is 2 to the 1, I guess. That's equal to, well, 2, right? So we're looking at these two numbers and comparing them modulo 7. 128 mod 7. Well, I guess it must be 2. Since I know the answer, that's sort of an intriguing one to check. 128 mod 7. If it's 2 mod 7, that means 126 is a multiple of 7. I kind of not sure if I know that. 126 divided by 7. 7 goes in once, and then you get 70, and then you get 56. Oh yeah, 7 into 56 is 8. So yeah, 126 is a multiple of 7. That means this number is equal to 2, and so is that one. So there's an example of it. Because, you know, to do interesting examples of this, you end up with fairly large numbers really quickly. It's not something that lends itself well to just playing around. Well, yeah, I don't need to go into the proof of this general statement, but let me show you how it is that people make divisibility questions that you can prove by induction using this idea. If I take, say, x to the 11 power, and I subtract x from it, I know that this has the same remainder mod 11 that that has, right? So x to the 11 minus x, that's going to be something that's divisible by 11. Because when you have the same remainder and you subtract it, and 0 remainder, that means the divisibility sign works. So 11 goes into x to the 11 minus x. You want another example? 7 divides into x to the 7 minus x. 5 divides into x to the 5 minus x. It's sort of instructive to do a little exercise with this on your graphing calculator. So I think, yeah, let me open up the screen capture and we'll see that. Yeah, so yeah, here I am with a graphing calculator. Why did I want to do this? Well, I want to show you that x to the p minus x is always divisible by p for a couple of different values of p. The easy way to do that with a graphing calculator is to put in a formula. I want x to the, how about we do 5, fifth power, minus x, and then divide that by 5. If this comes out to be a whole number, then we were right, it's divisible by 5. And if you stick the table method, you see that indeed it is a whole number right on down the line. And we can go to fairly large values before we, well, we're not going to run out of steam at all. These are all whole numbers. So that helps you to see that this is true for p equals 5. Oh, sorry, I wanted to do y equals. Let's try some other prime. How about if we did x to the 2 minus x divided by 2. Now that's actually not surprising to us because we've already seen that x and x squared are either both even or both odd. So when I subtract, I'll always get something that's even. And so when I divide by 2, I'll get something that's a whole number. But let's just check. Well, there they are, whole numbers. I'm at a funny starting point, but I feel like I should back up to the beginning. What are those whole numbers? Hey, those are familiar, aren't they? Do you recognize the triangular numbers? The view may be a little small. Recognize the triangular numbers now? Yeah, so that indeed works. I can do just one more p to try to be, somewhat convincing. What did I do? 5 and 2. How about we do 13? Well, you got to hit an insert to get that to not overwrite our formula, and then we'll divide by 13. Look at the table on that. And, well, those have quickly gone out of a reasonable range, but they're still whole numbers until it passes that. Yeah, those are still just whole numbers, even there. I think beyond a certain point here, we've got more decimals than I can actually display, or more digits, I should say, than I can display. So it's not clear there, but certainly the first several that we saw were on whole numbers. So that's sort of convincing. So let's go back to the whiteboard and look at the proof for that. So I just misspoke a little bit when I realized it as I was walking from the desk down here to do the whiteboard scene. The thing I'm going to prove is not that general statement, but rather one instance of it. So I've written a particular instance of it for all x in n. 3 is a divisor of x cubed minus x. Yeah. So we'll prove this by induction. And then we don't have a sum to deal with anymore, so this will be a little bit more of a challenge. What is our base case? Well, we're quantified over all natural numbers, x. So the smallest x can be is 0. Our base case is x equals 0. And notice that x cubed minus x is equal to 0 when x equals 0. Well, just made a comma there. And one other thing, doesn't 3 divide evenly into 0? Yes, it does. Now, if you feel like that needs justification, you're supposed to name the k so that 3 times that k gives you 0. But that'll be 0, right? So I would say that does not need justification at this point. We've gotten used to this idea that I can't do 0 divides 3, but I can ask whether 3 divides evenly into 0, and it does. It goes in no times, and the remainder is 0. Okay, so that's the base case. It's done. The inductive step, what we're going to do is assume this statement is true at stage k, at some k down the road. Actually, I want to assume I've got a k that's different from the base case. So k is going to be greater than 0. And let me move to the top here. And that 3 divides k cubed minus k. That's our inductive hypothesis, that 3 divides evenly into k cubed minus k. Great. So what we want to do is show that 3 divides, well, this formula with k plus 1s stuck into it. It's probably worth writing a "we want to show" sentence here. I guess technically that should be made a parenthetical remark because it's not really part of the proof, right? I'm just kind of giving a hint to the reader that this is where we're heading. So I'm going to do a little bit of algebra here. Note that k plus 1 cubed is equal to k cubed plus 3k squared plus 3k plus 1. Am I a magician, or do you guys know this thing too? If you are taking the third power of something, you basically get coefficients that come out of the third row of Pascal's triangle. So 1, 3, 3, 1. And then the powers on the variable descend, starting at 3 and going down. The last one is 0. And what else? Well, that's all for this. So k plus 1 cubed can be written like that. Let me make that into a comma because I want to continue with this thought. So k plus 1 cubed minus k plus 1 what is that going to be equal to? I got myself a little confused, so I had to stop the camera and start over. I probably shouldn't have been, oh well, too late. Yeah, so we want to check what this is equal to, but I want to be just a little smarter. Well, I guess I'll do two things. One thing is I know the first term looks like this, k cubed, 3k squared, 3k plus 1. But I want to refer things back to the inductive hypothesis. So I'm gonna group things in a slightly strange way. I'm gonna have k cubed minus k, and then I'm gonna have everything else. And so k plus 1 cubed, in addition to the k cubed, it has 3k squared plus 3k plus 1. But we've taken care of the minus k, it's right here. We're also subtracting 1. So this plus 1 and that minus 1 just knock each other out. So you can double check this algebra for me, but the way it's grouped is very nice, because now we know that the inductive hypothesis tells us that this piece, k cubed minus k, that's divisible by 3. And this other part is clearly divisible by 3. It's got 3's on both of the factors. So this is equal to, well, let me be a little more formal. Since 3 divides k cubed minus k, that's our inductive hypothesis. Excuse me for abbreviating here, but inductive hypothesis. There is an integer. How does that work? You get an integer, oops, integer, let's call it m, because we get other letters used around, m, such that let's do a little erasing and we can finish that thought at least, such that k cubed minus k is equal to 3 times m. So the way we've worked things, we get that the thing we're after, being divisible by 3 at least, is kind of written that way. K plus 1 cubed minus k plus 1. Well, it's equal to k cubed minus k, which is 3m. And then there's also the 3k squared plus 3k. Just barely fits, okay? And thus, it's equal to 3 times one integer. So since this thing in parentheses is an integer, our result follows. I guess I'll try to hold myself to the same standard I'd like to hold you. We should make a formal conclusion there. So, yeah, since m plus k squared plus k is an integer, the definition of divisibility tells us that, that k plus 1 cubed minus k plus 1 is divisible by 3. And so there's our QED moment. I feel like I ought to take away the rest of this so that the finish of the proof stands there by itself. Ta-da!